Good morning. This is Pre Calc chapter 12.4, Limits at Infinity. And we are going to need some tools today. Definitely going to need one of these, unless you want to cube really big numbers in your head. And you need your notes out. And this is a great section. What happens at really extreme values on graphs is what we're talking about. So you're going to have some type of picture or some type of function. And there are graphical ways of determining limits at infinity and algebraic ways of determining limits at infinity. We're going to start with the graphical ways. So what would happen on a graph if it's doing whatever it's doing? I don't know what it's doing. Maybe it's doing one of these or doing one of these. I don't know. Maybe it's a I don't know. What's the graph look like? What we're going to talk about is what happens if you go way out on the graph. So, and you can only really do that in your head. This is as much a mind experiment as it is looking at the graph. So you're going to have to like visually see asymptotes and different things like that. So, for instance, let's take this one. This is Lace's graph, a rational graph. And what we like to do is we like to talk what happens at extreme values. And just looking at the graph, I can tell that this one has an asymptote. And maybe you don't know that for sure, but there's times, hey, you're just going to kind of go in and you're going to maybe assume there's an asymptote there for this stuff right now because you don't actually, I mean, maybe we should actually put up the equation so you could graph it and you could see that. But we're going to look at this part of the graph, and I see an asymptotal value there. I see something like that. And what we ask ourselves is, as we travel along that graph, let's go out to the positive way here real quick. Oh, right now he's on like that bike path that's flat and you're like happy. You don't have to go up a hill. You don't have to. It's just, he's just chilling right now. He's like, oh, wow, look here. I get to go straight. And he's going to go, he's going to go straight for a long time. And the question is, as I get way out there, what number does he approach? Well, whenever you have an asymptotal value in a graph, what's going to happen is those two values, they're going to get closer and closer and closer and closer to each other until you can't even actually see what the difference between the asymptote and the graph itself. So if we went this way forever, we would say the limit as x goes to infinity, the limit as I get really big forever, well, what would I get out of that? Well, this graph right here, it looks like it's going to approach a half. Okay? Likewise, going the other direction. It's almost, we talked about end behavior. We talked about end behavior in chapter 2, way back in chapter 2. As x goes to infinity, f of x goes to 1/2. As x goes to, and we even said approaches 1/2 from the top or approaches it from the bottom. It's very similar in concept to end behavior. But here I am on this graph. I'm going to go out to the left forever. And if I go to the left forever, we ask ourselves, well, what does it approach? Well, as I go left forever, it's going to get closer and closer and closer to a half from the bottom. So we would also say the limit as x goes to negative infinity is equal to 1/2. Let's do some more. Okay, here we go. As I go to the left forever, well, looks like there's an asymptote at 4. So the limit as x goes to negative infinity is positive 4. And the limit as x goes to positive infinity is also positive 4. Here's Donkey Kong again. Let's send him to the right. He's approaching infinity. He's getting closer and closer to 4. As he approaches infinity, he's going to approach 4. As he approaches negative infinity, he's going to approach 4. There are many times you notice the left-hand infinity, the positive infinity and the negative infinity, they are the same. That happens a lot, especially on these rational graphs. It won't happen all the time, but it will happen a lot. So let's go to the right. Let's go to the left. The limit as x goes to negative infinity, as x goes to negative infinity is positive 2. And the limit as x goes to positive infinity is also positive 2. And I should say right now, I'm just going to add one in here. Let's say we have a graph, and maybe the graph looks like that. Okay? Maybe that's the graph. And we wanted to talk about the limits. So I take the limit as x. Let's just go to positive infinity there. Well, there's no asymptote on this graph. It doesn't really approach anything. So I've actually seen this differently in a couple different books. Some books will say the limit as x goes to infinity on this does not exist because you're not approaching any number. Some other books will say, well, the limit as x goes to infinity, well, that thing's going up really fast. So the limit at infinity is infinity. It's going up real fast. And I'll probably bop back and forth between those two ideas. It kind of depends on what book, what Canvas quiz you're on. But I will specify as we go through that what is what. Okay? All right, so let's do some functional values now. Some values here. The function negative 2x plus 3 all over 3x squared plus 1. And I'm going to describe this to you in more of an algebraic format. Like, I can look at this and I can actually tell you what the limit is. In fact, let's go ahead. I want you right now to go ahead, and I think the graph will really help us on this. So I want you to plug it into y1 if you would. So take out your graphing calculator and go ahead and plug in negative 2x plus 3 and 3x squared plus 1. And I'm going to graph that. And I got a bump. I got a weird bump. I don't know if you can see that on there. Oh, that's not so bad. There it is. And it looks like my limits left and right, it looks like that graph is getting closer and closer to 0. But let's talk about why. So I can remember doing this when I was young. I remember like not remembering the rules maybe. But what is the idea at infinity? The idea is what would happen if I have a really big number. So one thing that you can do, and you don't want to do it too big, otherwise you'll lock up your calculator. But you can think about, well, what would happen if I plugged in a really big number here? What would the equation approach, or what would I get? So if I went to my calculator and I went negative 2 times 1,000 plus 3, and I got negative 1997, and I got 3 times 1,000 squared plus 1, and I got those two numbers, and I divided those two numbers. So I'm going to divide the first one divided by the second one. What I get is I get negative 6.6 e to the, see, I get a number that's a small scientific notation number. I get a number that's really close to 0. And if I think about it, here I plug in 1,000, and this number right here, this number is growing. This top value is growing because I plugged in 1,000. But here I got 1,000 squared. 1,000 squared. So this number is like growing, growing. And this number down here is like growing. Oh my gosh, this one down here is growing faster. See? And if the bottom is growing faster than the top, that's becoming a smaller and smaller fraction. That's becoming a fraction that's closer and closer to 0. So the limit at 1,000 is 0. And it really doesn't change if I plug in negative 1,000. The negative 1,000 here, that's still making the top grow. But the bottom is growing. The bottom is growing so much faster because of that squared. Now the 3 and the 1. Let's theoretically think about this. Let's say somebody owes you $1,000,001. $1,000,001, and they give you $1 million. Do you really say, hey, pay up, buddy, I want my $1? Somebody owes you $1 million, and you have $1,003. They owe you $1,003, and they write you a check for the $1 million. Are you really going to care about the 3? You see these constants out here at infinity, they have really no bearing on the problem. I mean, what's the real difference between 1 million and 1,000,003? For at infinity, it does. And just think about it at a trillion, a gazillion and 3. I mean, we're back to the little kid thing. Oh, I hate you infinity. Yeah, well, I hate you infinity plus 1. Ah, you know. I mean, what's the difference? It's the same. If you're at infinity, you're at infinity. So these have no bearing. So I can almost not even think about those. So the top is growing, the bottom is growing faster. I'm getting closer and closer and closer to 0. getting closer and closer and closer to 0. So if the bottom exponent is bigger, that's what happens. If the two exponents are the same, let's think about this now. We said at infinity, these two values really have no bearing on it. And this is growing the same as this. So this is like a million squared over a million squared. It's like a million squared plus 3 and a million squared plus 1. Who cares about the 3 and the 1? But now I have a 2 and a 3 there. I want you to try this now. I want you to see what you get. I'm going to do it also. I want negative 2 times 1,000 squared plus 3. And then I want 3 times 1,000 squared plus 1. And I'm going to divide those two. That divided by that. Oops, I didn't do it right. The first one divided by the second one. So I'm doing the top divided by the bottom. And I'm going to get a number. I want you to get that number. The number I got is negative 0.666666654. Now, what do you think would happen? What do you think would happen if I plugged a billion in there or a trillion? See, here's the essence of what happens. These two don't matter at infinity. A million squared over a million squared, since these two don't matter, essentially those wipe each other out, and I'm left with the leading coefficients. I'm left with negative 2/3. And it turns out, regardless of those, if these two exponents are the same, your limit at infinity is the leading coefficients, that over that. Okay? The last one. The top is growing bigger. The top is just growing, and the bottom is growing. So the top grows faster than the bottom because the top has a cube. 3 and a 1 are really insignificant at infinity, but I have a 2 and a 3 there. I wonder what happens. I want you to take the chance to pause the video right now, and I want you to plug in 1,000 right there and see what happens. Okay, I hope you had a chance to plug in 1,000, and I hope you notice the top grows faster than the bottom, and I don't even know what the number is that's on your calculator when you did that divided by that with 1,000 in there. But what I do know is this grows really fast, and when that grows really fast, what the graph is doing is it's going up really fast. It's going up towards infinity. So one book will say the limit does not exist. The other book will say the limit is infinity, and it really, honestly, it really depends. I think it's beneficial to know I'm not approaching any number, but the graph is approaching infinity. It's going up. The graph does not exist, or it goes up towards infinity. And that's what I get. Or down towards negative infinity. This one actually might be, with that negative 2 there, I'd have to look at the graph. Anyway, all right, so here's your rules for limit as infinity. Limit as h approaches plus or minus infinity. Let's say the degree on the top is bigger. Let's say 3x cubed plus 1 all over 2x squared minus x plus 1. Okay, the degree on the top is bigger. There's an example. The degrees are equal, like 5x cubed plus 2x all over 10x cubed minus 5. And the degree on the bottom is bigger. Let's go with 5x cubed minus 4x plus 1 all over 6x to the 4th minus 3x squared plus 2. So the degree is the biggest exponent, and the biggest exponent is like the king of the whole thing. It's like the guy that rules over. And at infinity, it is the one that's going to affect the graph the most. Okay? So whenever you're out at extreme values, the biggest exponent is the controller. And it turns out when the top is bigger, we say the limit does not exist, or we will say the limit is infinity. Okay? Rule. Top is bigger. Limit does not exist. When the degrees are equal, the essence is they're going to wipe each other out. Even if there's an extra x up here and there's not down here. When the degrees are equal, this one would be 5 over 10, we take the leading coefficient, or 1/2. Equal degrees, use leading coefficient. Coefficient. Okay, leading coefficient. I-E-N-T. I spelled something wrong there. All right, and the degree on the bottom is bigger. When the degree on the bottom is bigger, the bottom grows faster than the top. The bottom is growing. The top is barely growing. That fraction's getting bigger and bigger. The limit is equal to 0. Okay? All right, so let's do some of these. I have a book page. I hope you can see this. It looks okay. Let's look at this. Let's go ahead and say, you know what? We're going to actually, when we get to those that are going up towards infinity, we'll say both. It does not exist, and we'll say also where it's going for the graph. So we'll look at a couple graphs. We'll do a couple problems, and that'll be the end of this video. All right, here we go. So let's talk about the limit here. So here's 1. Maybe I can blow this up here a little bit. Let me see if I can do that. View, zoom. Let's go all the way up to 2. Oh, yeah, look at that. That's better. Kind of see that a little bit better on my video. Oh, yeah. Oh, it's a little bit of a glare there, but we'll make it through. All right, so here's the first one. The limit as x goes to infinity here, and as x goes to negative infinity. Well, as I go here, the limit would be 1. It approaches 1. So as x goes to infinity, the limit as x goes to infinity is 1. And the limit as x goes to negative infinity is negative 1. Here, the limit as x goes to negative infinity, we would say does not exist. And it even approaches negative infinity. And the limit as x goes to positive infinity, we would say does not exist, or positive infinity. We could say really either one, depending where we're at. Okay, here the limit as I go to negative infinity is 2, 4, 6, so it's 4. The limit as I go to positive infinity is also 4. Here the limit as I go to 2, 4. The limit as I go to negative infinity is 4. The limit as I go to positive infinity is also 4. It's approaching 4. Okay. All right. Now it's this easy. We're going to do this. We're going to do this algebraically. Okay. And what I would do is I would just watch and see if you can process what we're talking about, and then you can come back and look these examples over again if you need to. I'm even going to zoom in more. Oh, zoom! I'm gonna go all the way to 300. Oh, that's just perfection right there. All right. So the limit as x goes to infinity of 3x squared. So the bottom is bigger. The bottom is growing faster. The top really isn't doing a whole lot. This limit is 0. Here, the top degree is 0. The bottom degree is 1. The bottom degree is more. This limit is 0. Find the limit as x goes to positive infinity. Here, that's x to the first and x to the first. They have the same degree. When they have the same degree, I use the leading coefficients. These two, in essence, cancel each other out at infinity. They're insignificant. These two values right here are growing at the same rate. So I use the leading coefficient, which is 1 over negative 1, or negative 1 is my limit. Insignificant. Same degree, leading coefficient. Same degree. Insignificant at infinity, leading coefficient. These two are insignificant. Same degree. Use the leading coefficients. Negative 2 over 1. Negative 2 is my limit. So you can see these are pretty sweet. They don't take a whole lot. Same degree. Leading coefficients. Limit. Same degree. Insignificant at infinity. Use my leading coefficients. some more. See if we can find some more good ones. Oh yeah, here we go. All right, top degree on this next one. Top degree is more than the bottom degree. The top degree grows faster than the bottom. The limit does not exist. DNE. Top degree is way bigger, way faster. The limit does not exist. Insignificant at infinity. Oh, I got t's here, but I got squareds. Squareds are the bosses. Squareds do everything. So I look at their leading coefficients because they're both t squared. 6 over -4, -3/2. Degrees, 2 over -8, -1/4. Okay, ooh, that's an x squared, and that's an x squared. I wonder what I would get if I FOILed that out. I would get, if I FOILed that out, 2x squared, 2 minus x there, so I get 4. I get 4 minus 2x is minus 4x. I get plus x squared. And this I would get -x squared minus 3. I use the leading coefficients because I have x squared and x squared. The leading coefficients are -1 and 1, so my limit at infinity is -1. Here, if I FOILed this out, x minus 1, I would get 2x squared minus 6 on top. On the bottom, I would get x squared minus 2x plus 1. I have the same degree. I use the leading coefficients. 2 over 1 is 2. Limit is 2. Okay? Here, I'm just going to do this one philosophically. I'm going to do this one philosophically. I'm going to think about, okay, so here I have infinity. Here I have infinity that's going to be squared. So this fractional value right here is like 1, or like a number over a bigger number. That fractional value here is going to grow bigger, faster on the bottom than on the top. So this part right here is 0 minus 4. The limit is -4. Here I'm going to have squared and x squared and squared. So I'll have squared and squared. This will be 1x squared when I FOIL this out. So I'll have 2x squared over 1x squared, which will be 2 over 1 or 2, plus 7. This one's limit is 9. This limit is 9. Okay? All right, let's see where we're going. Oh, two more good ones here. All right, so I got this one right here. So here I have one that I have infinity. I got a really big number down here, so this fractional value is 0 right here, minus I have a t and a t, the same degree. I'll use the leading coefficients, 5 and 1. So 0 minus 5, I got -5 right there. This part gave me 0. This part right here gave me -5, so I got my limit as -5. All right, so equal, so 1 and 1, and that's 1x squared. So this part right here, leading coefficients are the same. I use 1/2. And these parts right here, this FOILed out is x squared minus 6x plus 9. So I have 3x squared over this. Equal degrees, I use the leading coefficients 3 and 1. I use 3, I got 3.5 for the limit. Okay? Last thing here is number series. What we've done is we have also done these number series, this a sub n stuff, and you can find limits at infinity for the a sub n stuff too, and it works exactly the same. Now, sometimes you might use number theory to do it. You might not just, you might not have a rule right there, but you can really think about it. And I'm going to do these kind of fast. I don't think you really need to copy these down. Try to understand some of the theory behind it. So 1 over a limit at infinity, 1 over a really big number Well, 1 over a really big number underneath that bubble is 0. I get 0 here. Because 1 over a really big number makes the fraction grow really fast, I get 0. Limit at infinity. Infinity over infinity, those two are insignificant. I got 1s. Answer is 1. In your head, the answer is 2. Squared, squared, use the leading coefficients. In your head, number squared over number. Growing faster, growing slower. The answer is, does not exist. Okay, right here we have distributed 2n squared plus 2n all over n squared plus 10. Okay, n squared into n squared. I know I have numbers on here at infinity. They're insignificant. Use leading coefficients, 2. Okay, here I got 4 over a really big number is 0. 0 plus 1 is 1. And right here I got 1 over a really big number, which is 0, plus infinity minus infinity is 0. All right, that is the end of limits at infinity. Kind of a theoretical. The math is pretty easy if you understand the theory. This might be a video you want to go back and look at some of the examples again and really get in a groove and get the hang of it. But this is our last section for doing limits. So good luck and have a great day.